So basically, in each page you have an Ajax listener that listens to the likes, buttons, or whatever, so that you wouldn't be blocked on those remote calls. And in the background, it will tell logs of all the events into eventually an HDFS cluster. So that gives you a relatively easy way to collect the data from all those sources of those web pages, to collect the clicks. Once they store it in Hadoop, they don't really do anything while the data comes in. They just store it and forward it. It's a kind of a store and forward approach. Then they have two aspects that start to do the processing. One of them is called PTEL and the other one is called Puma. PTEL is basically do the aggregation, collect the logs and transform them into an aggregated counters. And Puma batches that and send that in 1.5 seconds into HBase. And HBase becomes a repository, the index of those counters. Okay, so that's kind of the approach. We'll, again, compare that to the tree.
Is 1.5 seconds, you're saying, is that?
That's the batch window. Basically, let's say that they're taking 1 million requests.
So the latency is actually 1.5 seconds to get the time you can
minimum, it's actually 30 seconds. Okay. They designed it to be 30 seconds, but the batch window is 1.5
but
seconds.
you could be trickling through these.
Exactly. There is more processing that is happening in the background until you actually see those graphs, those nice graphs. So they guarantee a 30-second window.
And it's just 1.5 second chunks, basically.
Yes,
okay.
Exactly.
Cool.
So the batches, by the way, it's a way to reduce the load on HBase. Because in this case, instead of having 10,000 requests a second hitting HBase, I'm having, by definition, not more than 1,000 requests a second just by going in that model. In this case, it's 1.5, so it's around 700 requests a second hitting HBase instead of 10,000. So batching is a way to do impedance mismatch of load between a system that is running fast, a system that cannot run as fast as the email. So let's look at Twitter. In Twitter, what we're measuring is effectiveness of a tweet. What are the effectiveness measurement of tweets? There are two common measurements. One of them is called reach, in which I'm posting a tweet with a link to, let's say, a blog or a news item. And then I want to see how many people saw that link. The other measure is how many people clicked on that and actually watched that. Okay? And in order to actually do that, if you think about it, it's and you don't do that in a kind of a Twitter style that I'll talk about in a second, it is a very highly computer-intensive operation. Because again, in a traditional world, MapReduce kind of world, think what I need to do. I need to find the tweet, then correlate, and find and get the follower of that someone who sent a tweet, and then find all the retweets of that tweet, do again that request and find the followers, and then I need to find the unique number of users that actually watch it, which means that I need to do the aggregation of all those different users and remove the duplicates and get the result out of that. So this is a fairly, if you do it in that model, it's a very heavy computation model, and that's how Twitter actually started. They even had a single server to do that. That's why the famous crashes of Twitter was, a lot of that was a result of that, because if Obama sent a tweet, all of a sudden, and you wanted to compute a reach, you crashed the system. So that's kind of the model of effectiveness for Twitter. And again, we're having very similar problems for different measurements, but the idea is the same. Okay, so you get a sense of what real-time analytics is all about. But let's see the approach that Twitter took. So what you can see is that they also was based on Hadoop for the batch system, but they took a different route to do the real-time aspect of that. And they use, for that, something that is called Storm, which is basically another way to look at that, is a pre-computed real-time view. In which case, I'm basically saying I want to compute reach, I want to compute the number of clicks, and I have certain part of my system that I continuously listen to that and producing those counters in real time. The difference, again, between batch system, the way to think about it is that in a batch systems, I'll give you the example of Google. When they use MapReduce, they were basically, the crawlers was collecting all those indexes, and they were rebuilding the index every 3 days, which obviously create that latency window. Today they're using something like percolator, so they're producing it in real time, which means that they're updating only deltas. So you have a set and view. It's much easier to work on that set and update it than to store it somewhere and then rebuild it, especially when you're dealing with a huge amount of data. So the main difference with an event-driven approach is that you're actually working on deltas and continuously update based on deltas versus working on the entire set, which is, in most cases, what MapReduce is doing. I would say the batch-oriented MapReduce. Okay? Some would call it a real-time MapReduce model because there is some similarity. It's still doing some batching here, but in a different style that fits more. And at the end of the day, just to finish that, at the end of the day, you could look at, from an end-user perspective, they produce the same result. It's a query on the data. I want to look at the data and see those counters and those graphs. So it's just a different view to query the data. And that's also an important observation. We usually don't think about those two things as queries, even though from an end-user perspective, they should be thought as the same thing. Yes?
Wondering what the frequency of the states was like. Is it?
I'll put some numbers. I'll put some numbers in that. But it could be, again, in a pure storm environment, without putting the edges into it, it could be even millions a second. Obviously, when you put the edges, which is the reasons why we're having a stock in the first place, things get slower because you're as strong as a weakest loop. Okay, so if we compare the two approaches, again, that's my analysis, we'll get to the real-time view of the Facebook approach. I think that the benefit that they have is that they have one architecture, one system, one underlying architecture to serve both the real-time and the batch system, which is a operational advantage. But in their sense, because of the way it is structured, the resolution of real-time would be thought in seconds or tens of seconds. Versus in the case of Twitter, it could be thought as in milliseconds even, and much faster, and obviously we can deal with larger volumes of data. That's really, at the end of the day, the bottom line, that's really the main difference between the approaches. Okay, so let's move on. So again, just to zoom into our talk here, we're going to talk about the Twitter approach, not the Facebook approach in this talk. Okay? Let's talk about Storm. Storm is a framework that actually Twitter is using for the real-time analytics, not at the beginning. It was actually developed by a small group of people, a company that was called Backpack at the time, that Twitter bought, and that became Twitter Storm. And they're using it to produce a lot of that analytics. It's an open source project, and since Twitter is using it, it started to gain quite a amount of adoption. The main reasons why that project has been created is, if you're thinking about event-driven processing, one of the main problems with event processing is that it's not intuitive. It's not intuitive to think in event-driven way. It's more intuitive to think in sequential way, right? I'm doing a query, I'm getting a result. But doing a query in an event-driven way, you'll see some examples, requires some, I don't know how to put it in words, but requires different way of thinking and imagination, quite a amount of imagination. In many cases, you needed to be a PhD to actually write something that would work in an event-driven way. Previous to that, they were using message queues and workers that was listening to message queues, and a lot of the time they were spending on routing data and deciding which data goes to which messaging queues because the structure of those messaging queues was pretty static. And obviously you could imagine how complex those type of systems can become, especially if you want to apply changes. Okay? And changes are fairly frequent. So the motivation behind Storm, if I want to put it in a very simple words, is to make event-driven programming much more intuitive and simple. And to deal with those routing problems and also consistency problem that usually happens when you start to do event-driven, which is parallelization, much, much simpler. And abstract that from the user so the user can query things much closer to the way we query that with other models. And a lot of that underlying structuring of how to route, where to route, what would be the level of parallelization that is needed to execute certain operation, when do I sequence, where do I put a sequential barrier to serialize some of the operation. A lot of that could be abstracted from the user because you want him to be focused mostly on the data processing of the story, not how you route things and not how you do the plumbing stuff. So that's kind of, I would say, the founding concept behind Storm. From an architecture perspective, Storm is built out of those main components. The Nimbus is basically the router, if you like, the broker of that system, and we have supervisor, which is the worker, and Zuckerberg is the state that the Nimbus is using to actually know where to route the data to, basically. So those are the components, and it's designed to be something that you could run also on a desktop in a single instance kind of model for development purposes, but also on a large cluster environment using, again, similar tools. There is a lot of thoughts about parallelization and how you speed up things through parallelization, so it was really designed to be very, very effective on the way it utilizes multi-core and distributed environment. Other concepts that are important to understand when we're talking about Storm is how Storm is being structured and how do we build a topology in Storm. So in Storm we have several concepts. One of them is called stream, which is basically your data input. The data input, the elements of the data is called tuples, which is basically a list of values. And we have spout. This is where your logic happens. This is the, say, the more important piece in that environment. The rest is kind of less important. So the bolts are the places where a lot of that logic happens, and those are the really important piece. The spouts are an abstraction for the stream. And topologies is a combination of those streams. So basically, you'll see when I'm calculating a reach or when I'm calculating a count of a specific things, it would usually be a pipeline of those spouts and bolts. This pipeline that produces a certain counters is usually packaged in a topology. And so everything is basically baked in a topology. So when you write something to Storm, you build a topology, and then you deploy it. And then once the stream is happening, it's actually aggregated. You could think about it as a more, again, glorified version of store procedures. So if you know store procedure from a database, usually store procedures are triggered when you write something to the data and you provide a template. It's kind of taking similar action. Okay? You're putting data, and it's continuously calculating it in a certain pipeline, in a certain sequence. Okay, let's take an exercise here. One of the hello world of event processing, especially in this case, is called word count. That's going to be hello world. So that will give you an idea of when I said that it's not that intuitive to think in event-driven fashion. We'll think about that problem and you'll see what I mean. Okay? So what do we need to do to actually calculate word counts? And again, just to put some data into that, let's assume that we have a stream of tweets that are basically strings. Those are the tuples that I mentioned, of words. And now I want to say how many times the word Nati was there, how many times the word Dwayne was there, how many times other words was there, and have a list of key values of words and number of the time that this word appeared. And then I can have this nice graph of, bigger words, smaller words, that basically weights the actual appearance of that word. Okay? So let's take that problem and see how do we program it or think about it in an event-driven fashion. How would you do that? I have a stream of data. What do we do first?
Parse.
What is it?
Parse.
Parse. Yes. But what do I do with that? I'm parsing it, and what do I do with the parsed data?
Stream of words now.
Exactly. So I'm taking a sentence and I'm breaking it into words. Okay? Because I have a string round of different words. The first action, I need to split it into individual words. What do I do next?
You should probably cluster similar words. You're probably going to want to do a reverse lookup table because there's far fewer total words than there are sources.
And why are you saying that? Obviously, you know the concept already, but why are you saying that? So let me take a
Oh,
step
I'm
back
sorry,
from
here,
what
I
you said,
should let
because
you-
I think you ran a little bit faster.
Yeah.
So the first thing that we did is parse it and split it sentences into words. The second thing is that we need to count them. But what happens if we count them unordered? Let's say that I have the word Wayne happens first, and then it goes to here. And this worker is actually taking it and updating a counter that says Dwayne 1. Now I have another stream that says the word Dwayne. But in this case, we routed it here because it's parallel. So this one has Dwayne 1. How many Dwaynes do we have?
2.
2. Who knows that? No one.
Yeah.
Exactly. So each one of them think that they only have one Dwayne. How do we solve that?
Reduce.
You don't answer. So, yeah.
Sort them.
Solve them? That's one way. So one way to solve it is by, that's kind of an afterthought, have the problem and then try to fix it. But how do we prevent that problem for appearance? That would make it much simpler to solve it. Let me give you a hint. What would happen if we'll make sure that when word comes in, it always goes to here? Do we still have problems? Exactly. So we need to do some sort of a hashing model to make sure that when a certain word comes in, it always being processed by a single worker. And this is, in an event-driven model, is ordering. Okay, so event can be unordered, in which case I'm maximizing the parallelization. But when I'm starting to get to the point, usually it's deeper in the processing, I'm becoming more stateful, and when I'm becoming more stateful, ordering becomes a way in which I can process states without losing consistency or without losing data. And that's how you solve that problem, and that's how you think about it. Okay? So you need to think about, first, how you might, do I need ordering? And if not, I'm maximizing prioritization. If I need ordering, then I'm starting to serialize that processing. And then I'm thinking of what would be the level of sequencing that I need to do. Is that in the case of Word, there is no that question, but in a more complex processing, you'll see that at some level I'm starting to serialize at that level, and then when I'm going deeper, I need to batch other things and other things. So the sequencing becomes deeper.
Stemming, or you just using pure words?
What's that?
Are you doing any stemming on a word, or you just doing words?
Am I doing what?
Stem.
Stem?
Stemming,
Stemming.
like running, swimming.
Oh, no.
Just
In this
pure
case, they're doing hash model.
Oh, okay.
Yeah, that's simple. Simple.
Are you just having a fast distribution, or?
Yes, that's the topology. Well, I should say that the topology itself is fixed, at least right now, it's strong. So you can't change the topology after you deployed it. The only thing that you can do is just rerun the topology and then route it to that new version. So it kind of knows how to do the hash modulo and how to make sure that those things are routed. That's why it uses Nimbus as well to maintain that state of which worker is dealing with which, is tagged with which number that is then being translated into this hash. And your question, of course?
Go ahead.
Okay.
So with the model, then you may saturate one worker with
Yes.
if it's not there.
Yes. That's always the case, by the way. There is no solution for that. But the only solution for that, I mean, you could always get to that point. The main solution to that is that you try to maximize parallelization and push serialization as deeper as possible so that you will lose that contention. So for example, in the case of word count, we'll maximize that. And in that case, we leave the amount of work that we have for that serialized process to be as minimal as possible so that it wouldn't become a contention. That's the way we deal with that, but theoretically, you could always saturate the system.
Now, are we talking about just for counting? I mean, we can add probably millions of numbers a second, but for something where there was some more complex processing, I would imagine you would want capability to have like a round robining.
Yeah, there is this aspect of round robin. Again, for the case of this presentation, I didn't went that deep, but you could do much more complex processing with it and build much more complex graph that has dependencies that feeds one graph, that one topology could feed another topology, and so forth.
But is this concept of being able to say, okay, it's just a flat hashing model, that's fine, but does Storm also had it baked in that I could say, you know, give me a round robining factor on something that exceeds a certain frequency, or does it have?
I'll show you how Storm, I mean, you don't talk about in hash modular terms. There is another way to express it. I'll show you how you do that. You basically give him the name of the field that you want to order by, and you don't really need to know necessarily the algorithm that he's using to order it. Let me show you the code, and I think that will kind of give you an idea of that. So let's see example. First of all, you can read it and understand it. That's something that if I would use it with JMS or Kafka, no way. First of all, it wouldn't fit into a slide. It would fit into the entire presentation. And second, you wouldn't be able to read it and understand it. So that's a big plus, which is the main mission statement behind the project. And what you can see is exactly what we showed in the graph. We had a splitter, we had a spout. We set the spout just to get the stream in. So that's the first step, which is more of like a technical step. But then we have two steps, split and cut. We're missing one step, by the way. Do you know what? Let's say that at some point we want all the words to go into one place. So it's the aggregation of the words into an index or some sort. Because right now we can't really go somewhere and have all the words available to us.
What are these integer parameters?
It's a hint on the level of scalability, the number of workers that you can actually split that work. So you could have a level of scaling depending on the step that you're in. That's when I said that, you know, in order to avoid that problem or reduce the chances for that problem, you could define the level of parallelization in each step differently and at least reduce it. But you
So
could
the
very easily program it or design it in the wrong way and be situated, as I'll show you in a second. So in your case, for example, in this case I did shuffle grouping, which means that I'm doing round robin. In this case I'm doing field grouping, which I'm doing that FIFO based on that work. Okay, so that's kind of gives you, and those two factors control the level of totalization.
And these are names that we're giving them. That's why, like on the second one, we're referring to the spout, which was the name of the first one. That's why the third one we're referring to.
Exactly.
The
So this one is basically taking things from
yeah.
here, and this one is taking things from this. So you started to get the idea. You'll see that there is even a high level abstraction to that, which Liwen will show in a live demo. So you'll see the live demo of how we do this. This is a little bit more complex processing. I'm not going to go through that right now, but generally speaking, what we're doing here is more steps in the process because it's not enough for us to get the tweets and find the followers per one that sent the tweets. We also need to do the distinct. So we need to aggregate them back. And the way we do this aggregation, or second level aggregation, third level aggregation, is just another step in that code that we've seen. It's just another pipeline that listens to the input of the previous pipeline, and you basically get the result of this line, feed it into that, and that's how you build a pipeline. Well, still, we're in a big data conference, and the question is, where's the big data? Because what we've seen in Storm is things that gets to events, and how many data can we store in events. So the data needs to be stored somewhere so that we'll be able to do some more aggregated analytics. And rightfully so, there is a missing piece in the puzzle here. Storm is a very light project. It's 15,000 lines of code, if I recall correctly, from the latest number. And what it tried to do is really focus on the event processing of the story and provide good interfaces to the streams and to the data store. And then you have plugins of those data stores. What does it really mean? It means that the end-to-end latency is not how fast Storm can do things, it's how fast the stream can fit in. Plus, obviously, this, assuming that this is not a bottleneck, then it's also depending on here. Usually this will become the bottleneck, but this may also be the bottleneck as well in some cases. Okay. But the important thing is that that's a real-time system. It's not yet the BI system because we still have the long-term data here. But this is the real-time system, not this. So our overall throughput is the end-to-end thing. To give you some real numbers behind it, and some other aspect that we need to realize when we're talking about Storm is that because of that, first of all, Storm assumes that when it delegates a request, it's mostly successful, and its high availability, if you would like, model is that if it failed, it could replay the event and do some sort of an idempotency model to deal with that. I'm not going to go through all the limitations. I'll kind of jump for the sake of time because I do want to leave Dwayne more time than before to show the live demo, which I think will explain things. But this is a very typical scenario in any event system, by the way. Not excluding Storm. Is that what we see is that people are plugging Kafka and Cassandra and looking at the Kafka webpage, and Kafka would say, well, we can do millions of events per second. We're the fastest messaging system in the world. Cassandra would give a benchmark that shows that they can do millions of operations a second. You plug them in together, and the system crashed. Why? Because in real life, when you're getting this amount of data coming in, and the other system cannot cope with that volume, then you start to pile back up to some capacity, and if nothing releases that, if it's a continuous stream that does that, you'll exceed that. Storm has some properties to control it, meaning that it could actually, you could say what would be the buffer size. In that case, it will actually reduce the rate in which you could push things. But that means that the limitation of that rate is going to be based on Cassandra. In this specific case, you go to 5,000 operations per second on a single machine.
Does it have a blocking queue that will throw away overflows with warnings or something?
It's not. It's actually throttling at the input, so it wouldn't consume them at the rate if it doesn't.
Right. I mean, that's what a normal blocking queue does.
Exactly.
The put will just block until it's empty. But I'm saying, do they have a model where you can just decide to just let it overflow with warnings? Fine, throw them away.
It does. I don't know. I think that the only thing that I've seen for controlling
I don't
is
think that would be
controlling the
built
size
into
of the
Storm
queue.
anyway. I think it would
Here's
probably
the
be
problem
built
is
into
that
the,
just pushes
into
the
the
backups
system.
down the line.
And
Right.
Somebody's going to
state
crash in a model where
provider.
you can't consume things as fast as they're being
Right. So in
processed.
that case, again, the only control that I've seen is that the limit of the buffer that they have, the queue that they store things, and if you exceeded that, then basically stop the
Storm pulls, basically, just to be
Oh, it
clear.
pulls.
You don't push into it, it pulls. So it's, when you give it a spout, it's reading as fast as it can,
Got it.
basically.
But then the source could still pull in things faster than what Storm pulls. So you
Right.
can still have a
That's what
problem.
I'm saying, it pushes the problem
Yes.
upstream. That
Yeah,
way
yeah,
overflows.
yeah,
Yeah, I mean, ultimately, something's gonna have a limit.
Yeah.
I think what Jeff's asking for is a feature some successful load shedding, trying to throw away a certain proportion of the data.
Yeah, in finance, by the way, it's very common in financial world that the throttling, most sophisticated throttling model is very common because
And routers will
When
do
you go
that
in
on the
there.
internet, right?
exactly. But I don't know. I don't know that there is those sophisticated throttling models in Storm. Maybe there is.
Storm has reasonably sophisticated throttle with the acknowledgement process.
You mean the ability to say when I committed something that I committed? That's
No. The ability to say there's a limited number, tuples outstanding.
yeah. That's what I
So
said.
that's,
Yeah,
okay.
that's what I said.
Okay.
When we talked about more sophisticated, we talked about more sophisticated than that you could say, I'm willing to throw some of that data, and which data I'm willing to throw. And that decision, I don't know that there is such thing to do that throttling at that level of control. So, we basically have seen a classic pipeline problem, right? I have one guy that can work very fast, but he's dependent, he needs to deliver the work to someone else, and we're strong as the weakest link because the guy that I'm delivering the work to can work at a much lower pace. That's going to be the throughput or the capacity that I'm going to be able to deliver at the end. And the same thing if I'm dependent on the materials that I'm going to be getting from someone else and he's not shipping it to me at that rate that I'm producing stuff, then I'm going to be limited by that. So it's a classic pipeline problem, and one of the ways to solve a pipeline problem is look at the pipeline and see how we can shove in things that will perform better. That's the simplest way to solve it. And memory happens to be that faster thing, okay? Because both Kafka and Cassandra happens to be dependent on file system. A few things about memory, speaking of memory. It's a few facts that even I was surprised to see when I actually put that slide together. One of them, that there was a survey recently, and actually I saw today a survey done very recently, not even public, by Gartner, that showed that organizations are actually looking at in-memory databases in general terms very high in their, it's very high in their priority. The other thing is that not many people realize the difference here between disk access to that. And by the way, when Kafka is saying that they can do that amount of performance, it's mostly because they rely on disk caching, which means that it's questionable what will happen if you actually unplug a machine and when it persists, is it really persistent? Because this is the physics of this. You go into a disk, this is the latency of this, which means that if you're syncing data to disk, you're in the worst case, in tens and hundreds of operations a second, not more. So everyone that is claiming that is doing more is basically not syncing to this.
Well, or is not doing random access.
Or even if it's not doing random access.
Or is doing.
Wait, what type of,
somewhere,
what kind of
somewhere someone is doing a caching.
Well, no. In the mode where you're doing stream processing and you're doing like a batch transfer of data, you have one seek, and then once you do a seek on a spinning hard drive, it can basically pour out data at like 600 megabit a second. So
yes,
I'm saying in a random access model, I'll buy that.
Right.
Yeah. Okay.
Okay. So back to that. Well, I'm not
Oh, it says random seek. Sorry.
Yeah. I'm not gonna get into that because I have some things to say about that, but that's gonna take the discussions completely into.
There's also group commit.
What's that?
There's group commit where you commit many threads work in one seek, and that gives you much higher throughput as well.
Right. But the question is, when you apply the machines, how do you know at what state you are?
Well, he's saying random seek there. It's in
No,
parentheses.
even with random seek, if you do group commit, and so you group many transactions together in one write from multiple threads, they all hang for 10 milliseconds, but then they all release together.
Yeah, right.
So the amortized cost is much lower.
If you apply something, how do you know which one finished to actually do the sync and which one didn't?
They all finish at the same time because they all finish
But you don't have the disk.
in the same sync.
Yeah, but you assume that you were able to order it before, but it could be before you were able to order it. So that's physics. That's physics. We're not going to argue about that right now, but we can discuss it later. The other aspect that I wanted to kind of go through is how do we plug in memory into that system? So obviously, if we plug in memory and that memory is not reliable, we're maybe making it faster, but we're going to lose data. So we need to plug in memory in a way that will be still reliable and transactional. And not many people know, but there was for a long time a concept that is called in-memory Datagrid that helps you to manage the memory resources in a reliable fashion. It basically does a lot of things that NoSQL does for file system, just in memory. Almost exact same algorithms, with one main difference. Unlike file system, I'm not trying to prevent access to disk and have Bloom filters and all those type of algorithms that I don't really need in memory. I can actually access data by reference, and that's a big difference. I can do also things that will allow me to speed up things because I can actually, because the data lives in the same address space as the application, as the code, in this case the Storm code, I can actually speed up things by pushing the logic into the data and do things more sophisticated. And by the way, this is where you get the tenfold difference in performance, more than it is to the I/O access in the case of memory. Yeah, that's me. Okay. So if we have that in place, then we basically took a bumpy road and replaced it with a faster road, and we get a much faster pipeline. Yes?
What are the economics?
What is?
What are
The economics.
Yeah.
Okay, we'll talk about the economics in a second, okay? Because I haven't finished that picture, because you're right. The question would be, and I would raise it if you wouldn't ask it, but it's better that you raised it, that we can't really use memory for our big data because of the economics. We can't really store petabytes of data in memory. It's not economical. And in some cases, not even physical. We really can't do that.
And it was where you also wouldn't want anybody to turn off the computer.
Yeah, exactly. So that's not a complete answer to our problem. That's a partial answer to our problem, so the question is where is the other part of that picture? And we'll get to that after this slide, okay? So the important thing in this slide, maybe I should have done it in a different order, but I still wanted to kind of map the topology to the Storm API that we've seen, is that one of the nice things in Storm is that it has a plugin for that input and a plugin to that output. So when I switch between, let's say, Kafka to, in our case, the in-memory Datagrid, or between Cassandra to the memory, I don't need to change my Storm code. The only thing that I do is a kind of a configuration change. I'm just changing the plugins for my input and my output, but the rest remains pretty much the same, close to that. So I would say, in reality, I'm minimizing the change. It's not going to be potentially a zero change. But in this specific case, it's a really zero change to switch between different underlying technology to a complete in-memory technology. So it's kind of an implicit optimization, and that's the beauty of that approach that I like so much. So to answer your question about the economics, we're not going to store everything in memory. And we're going to have another step in the pipeline in which we're going to have the data streamlined from that memory into disk. So the way we build the system is a kind of need to be thought as a two-tier approach, where some of the data is going to live in memory and streamline into our big data stream. In the case of Twitter, as you've seen, they even do this from here. So they send data here, and in parallel to here, plus here.
Now the routing that you talked
So
about.
for example, the reason why I'm saying that is that in Twitter, they wanted to, first of all, store all the records, regardless of how fast they want to process it, just for the record and for regulations and for other things. And on the processing side, they don't want to be locked here, so they do that asynchronously as well. Okay? So the fact that I can actually put data in memory, and it's not just messaging of that data, I can actually put the counters and do the processing of the counters, do a lot of things before it actually gets stored. I'm creating a much bigger buffer between the things that I can store in memory and do in memory, and when I'm hitting the disk. Okay? Otherwise, if the memory would be just a plumbing, a write-through kind of model, I'm still going to be very much dependent on the disk speed. Okay? But to your answer is that I can, just to give you some numbers, if you do the calculation, I'm doing 10,000 operations per second, and my index is still, let's say, 1 million key values. Those 10,000 still updates one value. So it's not accumulated. And I can store the entire Google search in memory. And as you've seen in Facebook, when you're eating Facebook, most likely your data comes from a memory cache, not from a disk. So that's how you tier those two things together. Yes?
Follow-up question. SSDs are becoming cheaper.
What's that?
SSDs are becoming cheaper.
Oh, that's a good point. Actually, this trip I did that work in which we're plugging SSD. So SSD gives you another layer here. So you can tier things into SSD. In my view, it's actually extending this thing than this thing, even though you tier other ones. And the reason why I'm saying that is that if you think about SSD, it's built as an array versus a disk, which is a stream. When you plug in SSD here, what those guys are usually doing is replacing a disk that is based on magnetic field, magnetic disk into a flash, which gives them some performance. I actually seen in the Cassandra Summit, the performance speed that they got wasn't substantial, it was mostly consistent, and that's the gain that they got, but not throughput. Because they still use a stream interface, and because all the upper layer assume disk. And that's the Bloom filters and all those type of things that you don't really need when you're accessing a flash. Where memory actually assumes an array, and a lot of the algorithms here plugs into flash much better than those algorithms. So in this case, if you actually need to utilize flash, you almost need to rip and replace the entire code and write it to flash, where in memory it's much easier to plug it in.
You can also consider tiering versus caching.
What's that?
Tiering versus caching.
Yeah. So I'm saying it would still look like that, because the cost of flash is still high. So all I'm saying is that the two-tier approach makes a lot of sense, because then you're maximizing throughput and cost. Because in this case, I'm actually reducing the cost for the high throughput side of that store, because I need less machine to do that processing. But obviously, I don't need to archive data and store a lot of data in that high SLA system. So if I have a two-tier system, I'm getting to the optimum cost of those two trade-offs. Yes?
Architecture question. So on each of these nodes, there's going to be this right behind memory cache. Does any separate process need to be run that memory is allocated in, or is that memory allocated off the same heap that's running Storm?
Oh, that's the same memory that allocates the Storm. It could also be remote. It depends on how you run things. It could be remote, or it could be co-located. It's more of a configuration kind of option.
Okay, so are there
The reasons why I would want remote is because, let's say that you're saying that the Storm is going to scale in a different scale than the data, for example. And in that case, you want to separate it.
I'm just thinking about practical things like limits on a Java heap on an older version of Java or something like that.
Yeah, so the way you deal with that with memory is that you have several things, but I'm not going to raise the
No, that was the main thing, is I was wondering if you had to start a separate
the off-heap things, but usually you could partition the memory into more processes, even in the same machine. And there are certain ways in which you could bypass that problem, but also Java is progressing. Now you have the better garbage collector to do those stuff things. So with that, I'll open the door to Gwen to show this thing actually working. Okay, so now we're going to take that conceptual discussion and see how we translate into real code, so you see that it's real. What it's going to do is actually run the word count demo. I'm going to use a Datagrid that comes from us. All of those components, by the way, are free. We're going to show it on a cloud, in this case on an OpenStack cloud based on HP. Unfortunately, we have a few tweaks to the UI that we didn't complete by today, but we'll give you a reference to the project, and in a few days, you committed to finish also the UI part of that demo. So I'll switch to
You weren't before you are
I may be committed.
I did have a question. If
Yes.
business spaces also has a MapReduce or a inline grid computing kind of framework,
Yes.
why would I use Storm?
Okay, that's a good question. And the main answer why we picked on Storm is that even though we have an event-driven model to deal with that, it's more, you need to write much more code to implement it, and you need to be a PhD to understand it. So for us, Storm is a much better DSL. And it plugs in very nicely because we're already designed for an event-driven model. It just plugs in into whatever we've done. Domain-specific language. It's a you've seen that. I mean, I can express a relatively complex event processing versus in all other mechanisms, including ours, you need much more code to actually express the same thing.
Repeat that question? Didn't hear it.
Yeah, the question was for us, Gigaspaces has some event models with the in-memory data grid that I showed. It also has some capabilities to do event processing. So the question was, why did we even integrate it with Storm? If we have that, and we could potentially do the same thing without Storm.
That's a good question.
Yeah.
I think we asked that internally quite a bit.
Yes.
Dan, I'm just not quite getting it. How does the bulk know that it's received every count of that word and now it knows to push to the next level?
Well, so the way the pipelining works, in this case, we didn't show that, but usually what happens is that each of those bolts is kind of a single task. So it gets a word, updates something, and then it finishes. And whatever the result of that, you'll see that there is a result. What's the output field of each? So each one has an input and an output. It basically produces the output, and that output gets into the next thing on the pipeline, or the next listener.
They're just working on one tuple at a time?
Yes. That's in the regular
Batch at a
case.
time.
You could, exactly. So you could also create checkpoints, which is called transaction in the case of storms. So you could basically say, I'm batching those, let's say, bulk of words for a particular session. And when I'm telling you to actually commit, then you're going to flash that, but at least I'm going to have a more controlled batching of those operations. So when Storm is doing that, it's not necessarily like it's doing this counting, and every time that it's doing those counting, it's pushing it to the next level. It's actually doing some batching, and then it's sending it in batches. But that window can be configurable, but you don't necessarily control it unless you're using a transactional vault. In that case, you could control it. Yes?
Are there any concerns about character set, your character set that you're using being agnostic, or will it work with, say, Arabic as well as, say,
Hebrew.
Latin script?
Yeah, yes. Because it's actually based in Java still, so and Java has this capabilities, so you could still do that. But it also works with Python and other languages, so it was really designed for that.
The word splitting isn't going to work, but otherwise Java doesn't care.
Yep,
I
exactly.
mean, just realize that everything that's actually done is written by you, for the most part.
Yep.
So it's not Storm's, job to write an effective word splitter for Arabic or something like that. It's kind of your job to do it. I was,
The other end has to have either Unicode or the language installed directly in order to.
Yeah, and Java is using Unicode, so the only place in which Storm can interfere in that is the way it's actually passing that thing, but usually it doesn't look at the data unless you're telling it which field it needs to route to, but then again, based on Java and Unicode, so it's basically pass it through.
right,
and
it doesn't have to be
interfere with
text, right? We're kind of hung up on text because that's the demo of it, right? You could be passing frames of video or something through it, I suppose, if they were small enough to make sense. Just to clarify the why, why does it make sense to marry these two and maybe to understand the difference? If you look at a data grid, it's focused on persistence. It's not focused on streaming. Even though it's capable of streaming, and actually in our integration here, we use it for streaming, because it is a highly available, high reliability storage system. It's got some serialization overhead. It's got some, you're making copies of things. Storm doesn't care. Storm doesn't have any state. Storm will just, if something goes wrong, it'll just reread a batch. So it's totally optimized for that purpose. And it's pushed everything else outside of its boundaries, basically, to not deal with that. So it gets the ultimate high performance. You're always dealing with co-located memory and logic. You're always reading directly from hash tables, not from some serialized storage format or something like that. So in theory, you can't go much faster than that, basically. Anyway, so this is a high-level view. What we've done is written a state store for Storm and a streaming source for Storm, so a spout and a state. So basically what we're talking about is the simple word count algorithm, where we're flowing data through an in-memory data grid to use it effectively like something like Kafka or whatever, some input for Storm, okay? So the demo actually uses the data grid as a FIFO queue for tuples into Storm, and then conversely, when Storm finishes the computation on the word counts, it's actually storing the word counts for every word it discovers in the text, putting that back in through an integration back into memory in the same location. There's nothing special.
Is that right to disk happening as well?
There's no right to disk. This is all in flight. So, the data grid does not really care about disk. This is another example of a system that pushes persistence onto makes it somebody else's problem, basically. So typically in the data grid, when you write into it, you've got a write behind mechanism, and that's when we get to talking about buffering. How much, obviously, if you take the weakest link in this system and you give it sustained load that the weakest link can't handle, at some point, everything will fill up. There's nothing around that. But for peak loads, having a large amount of data in memory, a large amount of space in memory, effectively to batch and to persistently store. Remember, we're not just talking. You talked about kicking the cord. What happens if you lose your data? Well, the key of the data grid is that it treats memory as persistence. So everything's backed up. If it's in memory, right into memory, it's making a backup on another node in memory, and so forth. So the idea is we drive Storm from the data grid, and we take the results of Storm into the data grid, which there theoretically could be served up by a UI, which in fact it is here, sort of, our management UI. Right now, what you're looking at is a HPCS. How are we doing with time? Am I got 30 seconds more?
Could it be a 10-minute demo? Or is that
Oh yeah,
okay.
no problem. It doesn't take very long. anyway, so it takes longer to explain it. This is our cloud orchestration product, Cloudify, and we're running a bunch of nodes, a bunch of VMs on HPCS. So there's nothing spectacular about them. They're all 4 gigabyte or less. They're not running, you know, cluster compute, you know, high-end processors or anything like that. No special networking. And the different components of the demo are the driver here, the stream driver, which in itself is running on 5 different servers. That's why you see 5 of 5 here. So there's 5 different servers. They're all going to be writing sentences that are pulled from the text of Moby Dick. I don't know, I just thought it was funny. So. And they're going to be driving that into XAP, into a streaming service in there that is compatible with Storm. And that's here. That's what's called ZapStream. And then these are the components of Storm over here, these 3. So this is very simple. So we only have 1 supervisor, which means 1 worker. Right? We have Zookeeper, which holds the state of the system, and that's pretty much it. So effectively what's happening here is the tuples are going in here, tuples meaning sentences are going in here, are going to go into this, and the Storm supervisor, which is running the spout, is going to be pulling them off in batches, processing them. Oh yeah, that was the other thing I was going to say. That the interesting thing is that streaming is batch. So, you know, the way Storm started out was read 1 tuple, run it through the topology, and then write it, and then acknowledge it, and go get another one. Well, that's pretty bad, right? So that's not good. So let's batch them, and then we'll read 1,000 at a time, process them all. That's okay. But now, you know, I've got a lot of infrastructure not available or wasted while this batch is passing, potentially from node to node, so let's pipeline them. So now I can build up a pipeline of batches, and that's really what Storm is doing. That's why you get these ridiculous numbers that are like clearly beyond what you could do writing onesies across the network. You're not going to, you realistically aren't going to get millions of tuples if you're doing them 1 at a time. So that's what's happening here. We're reading blocks of, essentially blocks or batches of sentences, breaking them up, and then writing the output. Now when we go to look, here's the UI for our data grid. This is just really quick, just to know so you know what you're looking at. This is the tuple. This is an object that's created just to represent the individual tuples as they arrive. This will rise as the flow comes in, and then this is the state item. This is the output from Storm. So now, let's see if it works. There we go. So what I'm doing now here is running a remote command on those stream driver instances. This is again from our Cloudify framework. So this is going to execute this stream driver is going to run for 30 seconds. It's going to, and each one of them, there's 5 of them, they're all going to run at 2,000 sentences per second, and then we're going to see what happens. We'll go back here and watch this. Hopefully it'll work. Sometimes it takes a while for the web UI to react here. There we go. There it jumped. So now you can see that we've got the accumulators here for the aggregators for the workflow. Tuples here building up. The aggregators are not going to build up that much. They're actually being updated remotely. Each one has a counter for every word. And in fact, if I go look at, I can go query these in real time. And I can see something like sucked has 5. I've got 5 demons driving this thing. So grapple, you know, 5, a lot of 5s.
So Moby Dick sucked.
Oh, there we go. There we go. That's a non-5. There we got, you know, Frozen was a little bit. Anyway, there's one of those for every, 27,000. There's probably not 27,000 words. My word split. There's colons in there, and it's kind of crappy. So anyway, we've done it all now. We did all, 30 seconds of 10,000 tuples a second through on just basically on 2 nodes. Running in memory. The aggregations are all there and available for querying. Of course, this is effectively a REST interface. Could be anything written on it.
You show the code.
So here's the actual topology definition. This is a little different. This is using the Trident stream definition. So rather than explicitly defining bolts and spouts, we do reference a spout here, but instead you create a stream, and then you actually have the operations here. So in this case, we can just read this. It's got a verbose programming, verbose, what's the word I'm thinking of? No, that's not the word. Anyway, fluent. Thank you.
I didn't say it. Builder?
Yeah, exactly. So you can gather it into what it effectively is a workflow here. Now, this may or may not be useful for every potential workflow if you're splitting things and they each go off on their own direction. But in this case, it's all pretty much a pipeline, right? I'm just defining a stream based on a spout. That's that XAP spout. If we look at the definition of that spout, right? And again, you can write spouts for anything that can deliver data. This is a Zap Trident spout, so it's a spout I wrote for Zap. The nice thing about Zap is it in itself is transactional. It can do batching, it can do FIFO and all that good stuff, unlike the equivalent Memcache. There's a Memcache implementation for state, but you couldn't use it for the streaming side, and then the state wouldn't be truly highly available either. So anyway, you go through each, and basically each line is an input, an operation, and an output. So I say each sentence field that's coming out of the spout emits sentences. I want to split large. This is a splitter I wrote because I didn't want to get every, like one-letter words in this because it would just be too much noise. So this is saying every word larger than 3 letters. I want to pull out of it. And then the output of that is going to be a word. And then I'm going to group by word so that I can then pass it to count. And then that is going to go into persistent aggregate, which a persistent aggregate will gather together all the stream components, if it's running on multiple nodes, which it isn't in this case, or multiple threads, and gather it into one place. In this case, it's running Zap state. This is just a static method for producing it's a factory method, basically. But anyway, so it, all the output is then written back into memory, so you've never had to touch the ground, basically, in the whole exercise. Right? You're reading from memory, writing to memory, and you do all your processing in memory. And I guess that's it.
If you want to pipeline it into Cassandra, that happens outside of the call-through configuration. You basically tell us up,
Yes.
which is the underlying thing. That's where the Cassandra will plug in.
Right, that was the asynchronous write bind I was talking about. So that takes it, you write into Zap, and then Zap can write to Cassandra or a database or whatever. Okay. And this is all available, I mean, whether you want the code or not, but the whole project, including Cloudify itself, is available on GitHub, and you can just download it and run this yourself if you're inclined.
So to wrap up, I would say a few things. I'll share some big numbers. Again, this will be the last slide for this talk. So what you can see here is two kind of benchmarks that I think would be relevant to actually get a sense of how fast it could go. So the fetch benchmark is the benchmark that we did with Cassandra, where we basically front-end Cassandra for read operations, and obviously we got in-memory speed to accessing data. So that graph shows the level of gain. So you can see in some cases it's a ridiculous number, and the reason why is because we're accessing in reads data by reference and not even going through a networking call. On the other case, we have a real customer that is using it for business transactions. So business transactions are actually doing, in this case, a load and match of data from a database, and in this case from an in-memory, and go to 50,000 operations per second on business transactions, which include a lot of operations in between, but that's generally speaking. So that's just to give you a sense of that. Now, the beauty of that, in that project, in my view, and the thing that gets me excited about it, is that nothing in your code changes to get that speed. You're still writing in Storm language, as you've seen. The only thing that changes is the underlying pipeline, if you like. You're just plugging in a faster pipeline, and all of a sudden your code runs faster. And I think Storm gives you enough abstraction that allows you to write the code such that you can do the type of optimization outside of your code and basically speed it up so nicely without, you know, locking yourself into a particular product or technology or online thing. So that's kind of I think, the end of it, and with that, we'll end that part of the discussion. Yes?
What was the y-axis on the circle?
It's the gain. I know it's a ridiculous numbers, but they're real. We used YCB, the benchmark for that, but again, there is it's open source, the benchmark is open source, so I can send the link of that as well. So you can see a huge number there. Again, the reason it doesn't really match it is just because we can access data by reference. We don't serialize it, we don't do anything on read operation. Obviously on write you get much lower, but still quite substantial. Okay, so any other questions? Thank you. Thank you very much.